This video is designed to help you with what are commonly known as wind and water current problems, where a boat or a swimmer or a jet plane or something like that is either flying or swimming or rowing or chugging along against a current or with a current. So this first example, and I'm going to try to use the formal way of doing these and maybe talk a little bit about intuition as well. A fishing boat is traveling 3 hours against a 6 km/h current. So let's write distance equals rate times time about that trip. So that's going to say distance, distance against the current or upstream. So I'm going to write distance A equals the speed in still water. I'm going to call R sub S. That's the speed at which this fishing boat would travel if there were no current. So for example, on a still lake or something like that. But this one is going against a current. So, and that current is then going to be subtracted again from the speed that it would go in still water. So if you think of one of those slide walks at the airport, if you're walking at 5 miles per hour and you step onto a slide walk that's going 2 miles per hour and it's going with you, then all of a sudden you're going 7 miles an hour compared to the ground. If you step on it, if you get to the end and turn around and try to go back, if you're going 5 miles an hour still at your walking speed, and now you're fighting the speed of the slide walk, you'd be going 5 minus 2 or 3 kilometers per hour, or miles per hour, excuse me. So in this case, whatever speed the boat would travel in still water, you need to subtract the current from it when it's going against the current, because it's going a slower speed according to the ground or to the earth. So R sub S minus C, this whole thing is the speed that it's going against the current. In other words, the speed that it's going if someone was standing on shore watching it, okay? And then, of course, it spent 3 hours doing this, excuse me. All right, so let's get rid of that arrow. And we're going to spend 3 hours going. So the return trip is the distance with the current. So this is going to be d sub w, and that's going to be going the speed in still water plus the current, because the current is helping it go helping the fishing boat go faster by 6 miles per hour, kilometers per hour, excuse me. And then the time is 2 hours this time. Now, this is being very basic. I'm starting with the general formulas and substituting in a little bit what we know. I substituted in the times, which we were given. Otherwise, I would just put t's in there, t sub a and t sub w for 3 and 2 respectively. Since I've substituted them, let's substitute what else we know. And if you read the problem carefully, you realize you know that the current is 6 kilometers per hour. So what we have is that distance against the stream is the speed in still water minus 6 times 3, and the distance with the current is the speed in still water plus 6 times the time. Now the only connecting thing that we still need is, because we're down to the R sub S on both the equations, that the distance is equal. But if we look at this problem, we realize the boat leaves someplace, travels out to a certain point, and then the return trip, meaning it comes back to where it started. Therefore, we know that the distances are the same. That means we know that the distance against the current and the distance with the current are the same. If we do some substituting, in other words, if we take that right there and substitute it in for d sub a, and we take that and substitute it in for d sub w, what we're going to get is R sub S minus 6 in parentheses, because you're multiplying that whole thing. That's the speed against the current times 3, and the speed with the current times 2. Okay, now we have one equation with only one variable in it. We can solve this. Distribute. You're going to get 3r sub s minus 18 equals 2r sub s plus 12. Collect your r sub s's. We'll collect them on the left side. So subtract 2r sub s from each side. And when you do that, you get 1 r sub s, which is nice. We don't have to worry about dividing by how many r sub s's we have. And that's going to equal 12. Add 18 to both sides, and you're going to get the equation that r sub s equals 18 plus 12, or 30. So what you have is that the speed in still water is 30 kilometers per hour. Now, you can double check that this is true, that this works, by simply saying, 30 kilometers an hour minus 6 kilometers an hour is 24 kilometers an hour. So the distance and the speed, the rate and the speed is 3 times, 24. That's the distance against, and that better equal the distance with. So the distance with is 30 plus 6, which is 36 times 2. And of course what we get is 72 over here and 72 over here. So it turns out that this boat goes 72 kilometers in 3 hours against the current and in 2 hours with the current. The next slide has another distance equals rate times time problem where we'll do the same kind of process and see if we can come up with the appropriate speed. So here's the second slide. It says a crew can row 60 miles an hour downstream in 3 hours and the return trip takes 5 hours. So let's do distance downstream, so I'll do down instead of with this time, equals 60 kilometers, it's 60, is going to be the speed in still water with the current times 3 hours, and then the distance upstream, so I'll call that U, is going to be the speed in still water against the current times 5 hours. Okay? So what we know is that both of these distances are 60. So we're able to put 60 equals r sub s plus c times 3, and 60 equals r sub s minus c times 5. Now, we don't know the still speed, and we also don't know the current. But what we can do is sort out these two equations more easily. And the nice thing that we can do is we can divide each side by either 3 or 5 respectively. And so if we divide by 3 and divide by 3, we're going to get that 20 equals r sub s plus c. And over here, when we divide each side by 5, we're going to get that 12 equals r sub s minus c. Now, this is two equations that we can solve simultaneously in a nice, easy fashion. There are multiple ways to do this. You can solve these using the addition method by adding the two equations together. You can also solve one of them by substitution. In other words, solve for r sub s. So over here, let's take a look at that. If we subtract c from both sides, we're going to get 20 minus c equals r sub s. And then we can simply plug that in over here for r sub s. And we're going to get 12 equals 20 minus c minus c. Now that's going to be fairly easy to solve. That's 12 equals 20 minus 2c. Subtract 20 from each side, we're going to get negative 8 equals negative 2c, and therefore c equals, so this is going to tell us that c equals, okay, we've done a little bit of lazy writing, sorry about that. C equals 4. So what that tells us is the current is 4 miles an hour, and we can plug that back into either of these other ones and see then that the speed in still water must, of course, be 16 miles per hour, or kilometers per hour, excuse me. Now, you can actually reason your way through this one as well, because if you notice between these two equations, something plus c gets you to 20, and that same thing minus c equals 12. That means r sub s must be halfway in between 20 and 12. If you average 20 and 12, you're going to wind up getting 16, which is, of course, the halfway point between 20 and 12. So that would be another way to solve this, is to simply look at it and say, I'm looking for the average. But notice that when we do these problems, you can reason your way through some of these. You can say, oh, it's going, 20 miles an hour downstream and 12 miles an hour upstream. And if you think, oh, it must be the speed in still water must be the average in between, because one is adding the current, the other is subtracting the current. You can do this problem all in your head and just say, oh, the average between 20 and 12 is 16. That would be a fast way to do it. But if you fill in distance equals rate times time properly, using this rate in still water plus the current and rate in still water minus the current as the two speeds, you'll be able to sort of do these kinds of problems properly each time, filling in what you know and then sorting out what you've got. So there's multiple ways to solve those two equations that we have here. I'll put an asterisk in between them, or a couple asterisks. When you solve those two simultaneous equations, there's multiple ways to do it. I showed it with substitution. You can also do it with the addition method, which you may or may not have learned at this point, depending on when you're seeing this video. And the other thing is you can just kind of reason your way through that. You can also, it's tempting to eliminate the distances by adding them together, but you'll notice that that would leave you with one equation with two variables. So you actually need to keep the information that one of the boats is going 20 kilometers an hour, one of the crew is going 20 kilometers an hour with the stream, and 12 kilometers an hour against the current. If you just use these two equations here, and try to set them equal to each other, since recognizing 60s are equal, you will get one equation with still two variables, and that isn't going to be quite enough information to sort it out cleanly. So hopefully this helped, and you'll recognize that the speed in still water is 16 kilometers an hour.